So, today's episode is the first one where I'm filming myself, which is nice. And yeah, it's called One Brain or Many. Parallel readers win, parallel writers fragment, and that's the whole decision. So, if you remember from the start of the series, I gave you the example of the AP agent. And this is us drawing it the way you would usually draw an org chart. So you have your manager agent, the same way you would have a normal agent. You have 4 specialists. Here you have your vendor, PO matcher, policy, and posting. Each one is basically imitating a certain action. All are able to talk to each other, as you can see here. And it looks like an org chart, of course. And this is exactly why this feels right, because you already know how to reason about org charts. This is something that in industry is very widespread. Now, here is what happens on Tuesday. You have 2 of these agents that independently decide that this vendor is new. So 2 vendor records get created. 1 invoice gets paid twice. And that's a huge problem because you're paying twice for the same invoice. And that's the duplicate vendor failure from episode 1. Except now the architecture generated it. So it's not coming from a mistake in the input, for example. It's really coming from a mistake in our architecture. So the question people ask is, how many agents should I use? And that question has no answer here, because you could also have more agents to control, and that could add more costs, and maybe that would reduce. So it's really, the answer for that question is, it depends. The honest version of that same question is, what work are the extra agents doing, reading or writing? So basically, if I'm adding new agents, what will they be doing? How would they be beneficial? And we can answer that cleanly because 2 of the best instrumented engineering teams in the industry publish findings that look like flat contradictions of each other. And this happened in the same week, actually. You have Anthropic that said multi-agents won by 90%. So they had the research and they said that multi-agents and agents controlling each other won by 90%. Here, of course, Anthropic is biased. And you have the team of Cognition that said do not build multi-agents, multi-agent system. So as usual, the question is, it depends what you should build. And generally, the hope of all of this channel and all of this series is basically to teach you the different use cases, the different techniques, the different ideas. And from there, you can make a better decision, a more informed decision when you're coming to your own project. And in a way, both of them are right, you know. You can build multi-agent and you can use, like, you never use multi-agent system. So the answer is always it depends. So here, let's start by what Anthropic actually built. And they had a win. They clearly had a win here. So they had the lead agent. So you have your lead agent. This is actually what you would do when you're writing code, actually. And the idea is that that lead agent would spawn sub-agents. And the critical detail is that each sub-agent gets its own context window. So like the lead agent would decide, okay, I'm gonna split this research part to the sub-agent, and then they're all reading, searching, fetching, skimming. Each one is doing their own thing at the same time. It's parallelizable, there is less latency. So there is lots of things that you're running here. And actually, even the result, the multi-agent system outperformed the single agent by 90.2% when it comes to their internal research evaluation. Their example task tells you why. So let's say they gave them the task, find every board member of IT companies in the S&P 500. That was their example. The single agent failed because it was slow, sequential searches. On the other hand, the multi-agent system split the action up and actually got much better results than the single agent one. And they explain the mechanism in one line, which is worth memorizing more than the example. It's the essence of search is compression. So sub-agents facilitate compression by operating in parallel with their own context windows, exploring different aspects simultaneously before condensing the most important tokens for the lead agent. So read what actually bought the win here, which is very important, and this is coming from this paper. What actually bought the win is the n context windows can read more than one context window can. and each one hands back a summary instead of raw pages. There is no shared document and no two agents taking conflicting actions, because the lead agent made sure to split based on the context. Split the context on, it made the decisions. It was like a planner for the other sub-agents. So it's just pure reading, and pure reading, of course, parallelizes beautifully here. So here, if we talk about price comparison, here you have chat, which costs, let's say the unit will be the chat. A single agent, if you ask a single agent to do a certain action, it would tell you it's 4 times more expensive token-wise than simple chat interaction. On the other hand, when you have a multi-agent system, you're spending 15 times the price of a single chat, which is of course a lot. So basically now you need to understand that multi-agent systems require tasks where the value of the task is high enough to pay for the increased performance. So you can't use it everywhere, you just need to know where to use it. This is the whole core of the decision, and why this is more like a maybe engineering, or maybe not even engineering, maybe even a consulting task, where you as an engineer, as an IT consultant or whatever, you are gonna have to take a decision that is dependent of the environment where you're put in. You're not gonna take a decision that's gonna solve all of your problems. And that's the issue that everyone in the industry are having today, is that they are all trying to take the same approach and just apply it. And they also actually measured where this variance is coming from. So the same, you have 3 factors that explain 95% of the variance. And this was on Broskamp, which is if I'm not wrong, this is a benchmark. And token usage alone explains 80%, with a number of tool calls and model choice who explain the other 15%. So just token usage alone, when it comes to cost, it's the most price producing issue. So basically here, what you're buying with multi-agent systems is you're not really buying more intelligence or better capacities. You're buying more token capacity, more context window, but like not really directly more context window, but in a way more context window. And that of course needs to be worth it. You can't use it for every task, especially when you're coming into enterprise AI. You can't think to yourself, okay, I'm just gonna spend whatever money I want, and I'm just gonna try to solve this problem. I don't care about the price. Now let's talk about the Cognition team. The Cognition team, which is the Devon team, if I'm not wrong, like I think it's a team inside of the Cognition team. And they had an example. Basically, they wanted to build the game Flappy Bird, and they wanted to build a clone of Flappy Bird. And the idea here, they had subagent 1, which they tasked to build the moving background with the green pipes. If you have played Flappy Bird, you have like a green pipes, and your bird needs to pass through these green pipes. And subagent 2 builds a bird you can move up and down. Okay, nice. Until here, everything is nice. What came back is subagent 1 misread its subtask. So this one misread the subtask and built a background that looks like Super Mario Bros, which would not work, because basically Flappy Bird, you have this pipe, this pipe, this pipe, and this pipe, and then you have your bird tack, 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 going through the pipes. On the other hand, like Super Mario, basically you're jumping over pipes. You don't have the parallel pipe on the upper part. So basically, the idea here, what you need to remember, is that it basically built the wrong thing. Subagent 2 built a bird, but it does not look like a game asset. Like, it basically built a wrong moving bird. And so the whole idea, I don't need you to remember the example, I just need you to understand that now the final agent is left combining these 2 miscommunications. So you have an agent who received these 2, and it's basically, it has like 2 parts that do not work with each other, and you're telling it, okay, make it work, And now they have people, and this is the important part, is that if you fix the obvious problem, you share the full context, you give to each agent, you give them everything, it still breaks. They're like, if you go through the wording, what they said is that you might end up with a bird and a background with completely different visual styles. And the reason is because principle, and this is the second principle of multi-agent system, is that actions carry implicit decisions, and conflicting decisions carry bad result. And this is the mechanism. It generalizes way past pixel art. Every write commit, every write, for example, if here the idea is to split writing between reading and writing. The Anthropic team did more of a reading action, and the Cognition team did something of writing or building, basically. Every write decision commits is basically a decision that was never stated out loud. So, for example, visual style, a vendor ID, a rounding rule, and happens when you're coding. And actually, I generally do not. And this is the reason, for example, you hear about Uber, and they said that they are using multi-agent system for coding. Frankly, in the beginning, and then they are asking themselves why this didn't work. Well, because they didn't read the research, which is stupid. But who am I to speak? I'm just some engineer in Germany. So you have your two writers that are making these choices separately, and no amount of shared context makes them agree, because nobody ever wrote the decision down to be shared. And the verdict in 2025 is that running multi-agent systems in collaboration only results in fragile systems. And this is something very important, especially if you're trying to build with your agents. Building with your agents, building with multi-agent systems is terrible, gives you terrible code and terrible features. The decision making ends up being too dispersed, of course, and that's the whole thing I need you to remember from this video. So, to summarize, and this is something I want you to keep in mind, you have two sides. As I told you, what Anthropic was doing their research on was the reading side of things. And it's mostly a breadth, like you have simple actions, you have multiple simple actions, and you're trying to read multiple sources and then summarize. On the other hand, what Cognition was doing was depth. It's more sequential work, it's not recommended to do it in a serializable way. So the idea here, the best tip that I can tell you, and this is my own synthesis. Of course, it's coming from research, but it's my own synthesis, it's not coming from papers. The idea here is that you need to parallelize reading and serialize writing. So this is writing, this is reading, and that's how your decision making should be done, even when you're deploying it on enterprise AI side of things. Extra agents may gather, analyze, and advise when a thread commits, but each access needs to be sourced. There is no single source states that has to combine everything when it comes to the writing side. So you need to have a linear side of things, and here you can parallelize, but these are two different actions. These two sides are two different actions. And this settles the question. You have 4 agents. When we are taking our example, you have 4 agents that are reading the invoice, the PO, the purchase order, the receipts, and the policy. And that is a good case, because here it's more, you're just fetching, not really fetching, but you're just analyzing data, not really in depth. It's quite simple data, and it's quite easy for agents to analyze this data. It's really not building or writing or really deep work. And so here it would be better to follow the plan of Anthropic. You have different parallelizable tasks. And yeah, this one is more if you're coding. Personally, if I'm coding, I do not like actually your own agent. If you're using Cloud Code, your own agent would launch different agents, but I always keep it to a single agent, because I feel like if I have, first of all, if I have multiple agents, the code quality degrades really, really fast. So actually keep it in a serializable way. People would say that I'm losing time or I'm not using the vibes well enough or anything, but I think the research backs me up on this point. So yeah, I will keep doing it that way. So here I'm actually going to explain to you a couple of benchmarks. Let's look here. You have a rule. And this is the idea of the first benchmark. A rule is only worth anything if it predicts correctly for the upcoming steps. So for example, we have the first benchmark, which is called Minecraft. This is coming from the game of Minecraft. Even if you don't know what's Minecraft, I will explain to you basically what's the benchmark. The idea here is that you get a target item and then an inventory, okay? And you have to emit the ordered steps that build a stone pickaxe. So you have these following steps, one by one, to be able to build a stone pickaxe. And this is from Minecraft. Anyone who played Minecraft would know what I'm talking about. Now, look why this is hard for a committee. Every step consumes the output of the part that is before it. If you get the order wrong, or if you have a committee and one side finishes before the other, and now you need to spend communication output so that these different parts of the committee, let's say you have 4 agents and everyone is doing one on each side. It's actually introducing more communication overhead than what it's bringing, okay? And this is clearly a sequential case. But now we have another benchmark, and this is something that you can see more in finance. And this is the finance agent. This is another benchmark. So, and for example, you have 4 different filings, and you have one research question you need to go and find out the solution for. And this is the good old answer. The thing here is that any order works. It doesn't matter if I'm doing filing D before filing A. It's not. So it's very parallelizable. So this is more breadth first, and this is a depth first question. Also, a depth first question or a situation has more, like the actions here are more complex than the ones in the breadth first question. And the baseline, so this is for the next slide. The baseline is, we're going to take the baseline. So we have these 2 benchmarks, and the baseline is what if we take one agent and the single agent is doing the whole task alone. So on Minecraft, these are the results. So single agent on Minecraft, these are the results for the single agent, and for finance agent, these are the results of the single agent. As you can see, the sequential side is doing better, because if you're a single agent, you're gonna do this, then this, then this, then that, then that. Yeah. So now let's look at this slide where we tested 180 agent configurations, 180 different configurations, and this is what we got. First, on a sequential task for Minecraft, the one that I showed you already, one coming after the other. You have independent agents. So if we go with a committee, if we have independent agents that are, for example, if you go back here, instead of making one agent do the whole of this, you make different agents doing this. We have a drop of 70% in performance. Let's say we have multi-agent system again, and the baseline here is a single agent, okay? Centralize, which means that you have a single agent on top, and then it's splitting different actions. We're getting still minus 50.3% from compared to the performance of the baseline agent. After that is decentralize. Decentralize meaning so we don't have each one of these agents is doing their thing, but they still communicate with each other. Independent, they don't even communicate with each other. Each one is doing their own thing, and then it's getting summarized. And for hybrid, you have a drop by 39%. So every multi-agent system variant here degrades performance by 39 to 70%, every single one, compared to the single agent. Now, if you do the same study, but you're going with this benchmark, the finance agent benchmark, you're actually winning performance. And this is the point of what all I'm saying in this series or this channel. It's really a case by case. It's a real discipline on its own. It's not something you're gonna pick for one side and say, okay, this is the solution I'm picking. And so for decentralized, like you have the agent and it's splitting basically like this. So you're basically imitating the format of the question, because this is a benchmark that it's not really like this is the shape of the benchmark, and you are basically splitting basing your architecture based on that benchmark. You're having an increase of 80.8%. So the rule is that we predicted, and it's holding here. Multi-agent is not a capability upgrade that you switch on. It's really a task structure decision. And on the wrong structure, it's not neutral. It actually is worse. So it's really an engineering question. It's not something you're going to just apply. Okay, I'm just going to use multi-agent systems here. Now, I'm going to make something like there is a case that's against everything that I've been talking about until now. So actually in Anthropic, in February 2026 of this year, we are in August right now, they did something. They took 16 cloud agents and they ran them in parallel. We're talking about $20,000, sorry. And they were writing C code. So actually pretty complex, like C is generally not considered, is more the more complex programming languages. So, and actually things worked out. So they were writing, it built in Linux. They were building like different known software like Linux, Postgres, FMPG, Redis. And they were rating it on the GCC torso. So there is an issue here. I just was talking to you how for depth tasks, it's really important not to have parallelism, right? But actually there are two conditions for that. First of all, we have a near perfect verifier. GCC is a known good like baseline or a feedback loop. And it's important that the task verifier is near perfect. Otherwise, Claude will solve the wrong problem. So here, that's actually the main reason why this worked out, which will not be always available for you. So this is nice, for example, in auditing, financial services, it's great to have. You will most likely have something like this. On the other hand, in the physical world for robotics, it's much more harder it depends on the task here. So it depends on the environment you're working in. Second is that the writes were partitioned. So they were actually coordinating by get log files, and they were not like negotiating with each other or talking to each other a lot. So each agent was owning different files. Nobody had the mutable record. They didn't overwrite each other. So that's more on the, like, it's one of the, we already have spoken about the main reasons of the failure of multi-agentic systems. And one of them is the communication part between the different agents. And Cognition actually names this exact property when they list these demonstrations. They all share a property. Most real software does not. A simple success criterion, as we are talking here. So you need to, if you're building multi-agent system, you need to always keep these two conditions, which is like, for example, is there a mechanical oracle for this invoice to be correct or not? This is for finance. If no, then maybe you should write it, build something that your agents can verify against. Do your agents write to the same record? Yes, that's a problem. That's another problem. You need to be sure that they do not overwrite each other. So that's at least for the architecture side of your agentic systems. Now the steelman does not, so this is what we call a steelman. So, and it does not break the rule. It just tells you the conditions under which you can have a success if you're writing a multi-agent system for a depth or like more like a sequential task or really not a parallelizable task. So actually after 10 months of that paper that we have been talking about from Cognition, where they said, do not build multi-agent systems, there was another paper, and it's not a reversal, about the same subject. And what they are saying is that the original observations still hold for parallel writer swarms. It is basically a narrower class of patterns. There is a group of patterns that actually work. And every one of them obeys the laws that we have been talking about. First of all, we have the read-only sub-agents. So search and code search, you have your search agents that are gonna go and do their search for you, and then you have your coding agents. And After that, we have the generator plus verifier agents. And this, we have been already talking about LLM as a judge, only is worth it after one loop of verification and feedback. So after that, we have a smart friend, which is a fast primary model that calls out to a stronger model on the hard decisions. So you have your weak one that's doing its actions. If it feels that something is stronger, it calls to upper echelon and asks for a stronger friend. Basically, there is a manager that does this decision. And finally, you have a manager that splits work and should report one channel through one channel, and where basically you have the manager and the children pattern. Here, all of these patterns we have been talking about in our series. And this is coming from the paper from Cognition too. They were talking about these are basically the main architecture that they work for multi-agent systems. The reviewer pattern, this one, has actually a number attached, and this is the most finding in this whole paper. On pull requests written by their own agent, the reviewer catches about 2 bugs per PR, and roughly 58% of those are severe. So logic errors, missing edge cases, security holes, and it actually works better when the coder and the reviewer share no context beforehand. So a clean context reader beats a colleague who watched you write, which is interesting here. So without context was actually the reviewer without context was doing better than a reviewer with context or with knowledge of what the main coder was doing. So yeah, the reason for that, frankly, it could be maybe not. Maybe it's like these agents are made to be more sycophantic and agree with what is already done, so they agree with each other. So I really do not know why this is happening, but it's something that's really interesting to keep in mind. And what stays actually is rejected. So in their own words, the unstructured swarm approach, arbitrary networks of agents negotiating with each other, is mostly a distraction. This is something that we have seen in big companies, in enterprise AI today. So yeah, always keep in mind, these are the 4 winners that we have until today. We are in August 2026. And I would always tell you to follow these patterns. So everywhere, a winner is extra intelligence and one writer. That's the pattern under all 4. You have one agent that's doing the writing, not all of them, and maybe extra intelligence on the verification, maybe on the having the smart friend. You call one that's stronger to do a certain task, but always keep that one writer. That's the common theme between all of these patterns. So in the end, I want you to keep in mind that there are 3 fences before you build a swarm of agents. First of all, multi-agent is not the same thing as orchestrator workers. So an orchestrator will be calling the subordinate and steps that report back to one loop. So there is the looping side of things with helpers. The sub-agents, so this pattern of architecture never talk to each other. So the sub-agents wouldn't be talking with each other enough. And of course, that's overhead, the communication. And the idea here is that you need to know when to use depending on a different situation. Most frameworks that advertise multi-agent shipping are not really multi-agent shipping. And actually, if you remember episode 6, we were talking about that. Like what's real multi-agentic and what's agentic and what's not. So second is the second fence before you build a real multi-agentic system is you need to understand that it's not inherently better. You just saw statistically compared to a single agent, it's minus 39% to minus 70% on sequential tasks. You have also more failures. So it's really something that you should only use in certain cases. Follow this before you realize which cases those are. Finally, it's not a human team. Whether we like it or not, today, we as humans, we communicate much better between each other than agents between each other. So if there are conflicts or PR merge issue or anything like that, at the end of the day, two engineers can figure it out. Like they will find different ways to figure out the best solution there, which is not the case for agents. Today, they are too sycophantic, they agree too much with each other. So those are the three fences you need to keep in mind. Now, let's do a fast recap about this whole episode. You have, first of all, parallelize reading. We had a 90% increase in performance compared to a single agent, which was amazing, but at 15 times the tokens. Then serializing writing. You have every action commits an unstated decision. Two writers make them separately and never agree. So having a single agent that really is conducting the writing or building is better than having multiple agents do it. Finally, it's a task structure call. So the sign flips. You have minus 39 to minus 70% on sequential tasks compared to single agent, plus 80.8% increase in performance with breadth first, as I said already, paralyzing for reading or that are parallelizable. So it's not really capability upgrade, it's almost something else. I'll tell you what is that something else. So the question was never how many agents it is what are the extra agents allowed to touch. So here, and notice every working pattern quietly assumed that the reader can hold what it read and the writer can find what was decided. So finally, for the next episode, we will be talking about the good old memory, what an agent keeps and what it loses. It will be a very important episode. So if you like my content, please like and subscribe and follow me on LinkedIn. Thank you.